Hello, and welcome to today's session of Enriching Your Data Stream Asynchronously using Apache Flink. I'm Hari Rajaram, and I'm a Principal Data Architect at AWS. And I also have Jeremy Burr. He's a streaming specialist at AWS. Let's go to the agenda. And in today's agenda, what we'll cover is we'll talk about the various use cases for enriching your data stream, when and why one should use an asynchronous IO when making an external call. And we'll also take a deep dive on how Apache Flink has its implementation for async functions and typical common patterns and configuration with respect to Apache Flink for making async IO calls. And lastly, we'll showcase, we'll do a demo on Apache Flink on Amazon Kinesis Data Analytics. Jeremy?
Thanks, Harry. So when designing your streaming pipeline, it can occasionally be necessary to enrich a payload that's coming into the stream with some external data sources. And so a couple use cases where we see users wanting to do this would be, for example, a financial transaction, say a stock market transaction where a payload comes in, a user just purchased a stock, and the financial institution would like to enrich that data source with some extra information like the user's location when they were purchasing the item, or some other relevant information. We also see this in media companies where maybe a user is watching a video, and that payload information is going to contain the fact that the user was watching the video, but they also would want to enrich that payload with something like the country of origin, the time of day, or some third-party metrics about that particular user that can't be stored in stream. And so to do this, a common pattern is enriching data elements using API calls, or queries to a database, or a key value store. And that's really what this talk is about, how to do this efficiently. So enriching your data stream must be done efficiently so as not to impact the payloads or the data coming into your stream. And when you consider how to design this interaction, there's really two ways to think about it. You can make that query to a data source synchronous. And that synchronous interaction, what it really looks like is when you make that request for that individual payload, that payload and the subsequent payloads that are coming into the stream are going to be waiting for that request to be completed to get the response back. And that's really not good for the performance of your data stream. We can try to improve this performance by scaling the parallelism of that specific operator. But of course, that comes with some high resource costs because you'd have to add more nodes to your Flink or your streaming framework. You'll add additional tasks or threads and have to ultimately maintain that ultimate interaction between all the additional nodes and overhead that you're introducing to your streaming workload. And we see users most often implement this using something like a map function or a flat map, where that map function would make that synchronous request to the API or database. Now, the other way to achieve this enrichment would be through an asynchronous interaction. And this would be where the single function that you are calling your database or API with would be able to handle requests and responses concurrently, meaning that when data is coming in, it's not waiting for the previous request that came through that enrichment phase to be completed. Requests can be sent to that operator as they come in. And so what this really amounts to is the fact that the time waiting for that individual operator will only ever be as long as the slowest request that's made in parallel. And what usually happens in this case is that it leads to higher throughput of your overall workload. And so users typically implement this using something like a rich async function, where you can define your async client as a shareable resource among the subtasks of that particular operator. And we're going to get into how that's implemented a little bit later in the discussion. But just to fully illustrate this point, this image really does a great job of illustrating the difference between doing synchronous IO versus async IO. So you can see on the left-hand side of this image, we have a message coming in, and then that red bar is illustrating the amount of time that it's waiting to be completed. And only after it's completed do you actually are you able to issue that second request and wait for its response. But in asynchronous operations, we can send upwards of, in this image, we're sending 5 messages in parallel and receiving those responses in parallel. So as we said in the previous slide, the longest time that you'll be waiting is actually amortized over time through the number of messages that you're sending to your data source. And this is really where the process improvement and the throughput is going to come. So why is async important for real time? Well, as we said in the previous slides, blocking calls can really stall your data flow. And if this API call, you would hope that it's fast, but if your API call is making upwards of 100 milliseconds, 200 milliseconds, or even up to a second of I/O time, that's really going to impact your throughput of your workload. So it's really important to avoid back pressure, and that would be of the upstream operators, not allowing them to send their data to the operator that's making this enrichment call. You can avoid that by making these requests concurrently. And in addition to that, because you can put the logic of the external data source into that query or into that other application that's managing that logic, you can actually decouple this enrichment logic from the streaming application. And in general, streaming workloads should not be concerned with handling these synchronous requests. It's really not what you want to get yourself into when you're designing a streaming workload. And that's why async is so important to making your streaming workload performant. So next, Hari is going to talk about how Apache Flink implemented async IO and how it can benefit your workloads.
Thanks, Jeremy. So what we will see here is we'll look at the internal architecture on how Flink has implemented or facilitated the async calls for doing async IO operations. So the crux of the architecture is async wait operator. So the async wait operator, it allows asynchronously process the incoming stream. So what happens is typically stream data is processed via process element call. And for each record, the element is added to the queue, and that queue tracks the in-flight async calls. And once it is called, the async function, that is the function that has been implemented by the developer, that would be actually called inside the process element. And async function, as Jeremy pointed out, it is a user-defined function that actually triggers the async IO operation. That's a call which you make it for your API. And typically you do it by a rich async function, extending a rich async function, because that's a variant of your async function which Flink community has already developed. And the advantage of using that is it actually gives access to runtime context, and you can actually even use it in your async function application. The method which you typically override is async invoke, and which you should override. And it accepts two parameters. One is obviously your input record, and the other one is the result future. Future is basically you wait for your result to come back from the API call. And there's another method called timeout, and this timeout is nothing but when whether should I timeout for X number of seconds when I do an API call. So that these are two typical methods which you overwrite when you develop your async operators. The next thing which you would see here is we will also see something called emitter thread. So what is an emitter thread? Emitter thread, it's basically a daemon thread which is inside your async wait operator, and it actually pulls the queue for the completed operation. Remember I told about the queue which is added with the process element. So once it's added to the queue, what happens is it actually async invoke calls are happen, but there should be somebody to emit the data, right? So what happens is emitter thread is the thread which actually emits the data to your next stream record or to the next operator. So what emitter thread has is it actually it does a lot of core functions. One is definitely it coordinates with your task thread, because it will actually state the task that, hey, you know what, my capacity is full in the queue, so don't add any elements to my queue. So that is one thing. And also it is kind of a blocking operation. When I say blocking operation, it is not extensive blocking operation. All it does is it actually blocks when an element is added to the queue. So that's what emitter thread is. So emitter thread is the core heartbeat of your async wait operator, which actually does the emission of your output records to your stream record. So the other thing, beauty of Flink, which we already know, is the failover, right? What happens if there is a failover that is happening, right? So when restoring an operator state, the in-flight generally the in-flight elements that are in the queue or is checkpointed. So when a failover happens, it actually takes the elements from the state, and then it gets elements from the queue, and it automatically invokes the async function, async invoke. You can clearly see here that the flow is the same. The only difference is when you talk about from a state, you can see that end of the day it calls async invoke, and the flow remains the same. There's no difference between an async from a state nor from a new element. The only difference is this is coming from state and the other one is coming from a process element. That's the only difference. As I said earlier about checkpoint, right? So checkpoint is done for all in-flight API calls that are in the queue. Remember, queue is nothing but a holder of the API calls that are in flight, so that it can track what has happened to my API call. So the checkpoint is done based, of course, on your checkpoint interval. It is done for all of your calls that are made to the API. So that's the core internal architecture. And what are the common patterns when using an async IO? Again, there are two common denominators which Flink community has given us. One is an ordered wait, and another one is unordered wait. What is it? So let's quickly talk about unordered wait first, so that you can understand what ordered wait is. So let's say in this graph you see 4 elements that are going inside DCBA, that is going serially to an async operator. Let's say your async API gave the result quickly for B, right? A came a little bit late. But what happens is in this point of time, emitter doesn't wait. Whenever it gets a result back from the API, emitter will output the data to the next operator or to the next stream record. So that's the unordered wait. Basically, it doesn't worry about the sequence of when the data came in. It just emits whenever it gets a result back. So that's what unordered wait is. On the contrary, order wait is even if I get the data back from B, what it will do is it will actually wait until I get the A result back. So that's what it in simple terms, based on the arrival to an async operator, the sequence is equally maintained when we actually do an order wait. And this is how typically you implement an order wait and an order wait. End of the day, it is just the function which you actually call. And that's what you can see on the code. And we'll also see in the demo on how it is done. So there are some key configuration and some tuning parameters which you need to consider when you actually do an async calls to your API. One of the thing, if you look at the previous code, you saw that there was two parameters called capacity and timeout. So capacity, right? If you remember my discussion, I told about the queue. So capacity is the capacity of your queue, so that how many elements can I hold into that queue, so that it actually tracks the maximum number of async API calls that are in flight. So that's what capacity. You cannot have a lower capacity. If you have a lower capacity, then end of the day you're making less async calls. If you have a really higher capacity, then you have to consider your checkpoint. So you need to make sure that your capacity is correctly fine-tuned for your API calls. The other thing is timeout, right? You cannot keep on waiting. I mean, of course, there is, if you can actually configure your timeout to probably even 10 seconds, but it doesn't, at that point of time, it doesn't make sense, because we are now talking about checkpoint again. Your checkpoint will actually grow. So ensure that your timeout is equivalent to the API timeout. Don't make it too high or don't make it too less. So ensure that your timeout is correctly configured. And behind the scenes, Flink takes care of timing out your API calls automatically. There are two critical functions, open and close functions. If you remember, I talked about rich async function. Rich async function has open and close implemented. But what happens if you want to talk to a database, right? At that point of time, you would actually ideally want to maintain a single connection, so that it is actually shared across for all your API calls. So I would highly recommend you to actually use open and close functions when you are typically making JDBC connections, or opening up any kind of connection pooling to any external database. So that is something which you should definitely do it. The other critical thing is operator parallelism. Parallelism, right? Parallelism in general, it's a instance of your a task that is running in the task lot. So with respect to operator parallelism, it's for each instance of that async operator. That's what operator parallelism is, and this is very critical to configure, because this in combination with your capacity plays a role when you make your API calls. Last but not least, checkpoint interval is very critical, because if you remember, I told about how capacity and timeout plays a role in checkpoint. If you have a lesser checkpoint interval, your payload to a checkpoint is very less, but you will actually make frequent checkpoint calls. If you have a higher checkpoint interval, at that point of time, your size of your checkpoint will grow, and then you would literally stall your flow for X number of milliseconds or seconds. So make sure that your checkpoint interval is critical, because remember, we are also checkpointing the in-flight API calls which we are making. So that's the reason checkpoint interval is critical when you do an async call. So next, we'll actually have a quick demo of async IO with Amazon Kinesis Data Analytics for Apache Flink. Jeremy?
Thanks, Hari. And yeah, I just want to showcase the Kinesis data analytics for Apache Flink with this async function that we've implemented. And so right now I'm on the Amazon Management Console taking a look at our Kinesis data analytics application. I've deployed a jar which contains my Flink code, Apache Flink code, and what this jar is doing. What this application is doing is pretty simple. It's reading from a Kinesis data stream with an operator parallelism of 1. And then it's actually splitting that stream into two separate data streams, one of which is running an async wait operator that we've been talking about for this presentation. And the other one is a map operator that is doing the exact same function as the async wait operator, except it's performing that synchronously. And so what these operators are doing is they are both making a API call to an API gateway, which calls a Lambda function. And that Lambda function, all it's doing is sleeping for 1.5 seconds and returning back the response through the API gateway. So this is obviously a very worst case scenario. And we just wanted to showcase this as an example of the power of async. And so we'll be able to see the differences between how async handles that versus the synchronous function operating in Apache Flink. And I just recorded a short snippet of the CloudWatch metrics that we got from this application. So let me just point out on this particular image, what I was doing, I was also plotting the capacity. We talked about the capacity in previous slides. The capacity in the first run of this application was set to 1. So in theory, these two operators that are split should relatively behave the same, right? Because capacity of 1 means there can only be one request made concurrently. And so we can actually see in this video that there's really no difference at the peak operation. They're virtually exactly the same in the number of records in and out per second between the map and the async operators. But as we increase capacity, so here I've just made capacity 2, and let me just go back a little bit. I made the capacity 2, and you can see that effectively we've doubled our number of records in and out per second in the async wait operator. And you can see this pattern over time. So I've set the capacity to 4, doubled the capacity from before, and we can see that multiple reflected as well in the async wait operator, number of records in and out per second, and so on and so forth. Now this will eventually cap out. And as Hari was talking about, the capacity really needs to be set to what your API or what your database or external data source can handle. You really don't want to set this to an insanely large number where your API or database is going to get overwhelmed, because that will, of course, have negative effects on your database as well as your application if that were to be detrimental. So I just want to go back to the management console to showcase another couple of things that are really great about Kinesis Data Analytics. So the first thing is the snapshots. So when you're running an Apache Flink application in Kinesis Data Analytics for Apache Flink, there is an automatic configuration that will snapshot your application into Amazon S3. And of course, you can deploy your application with snapshots. There's a configuration to do that, and it's all API driven. And we can also monitor our application's performance through the use of CloudWatch. And that's actually what I was showing in the previous video that we were taking a look at. So on the subject of scaling, there's an auto scaling feature within Amazon Kinesis Data Analytics, which will scale your application's parallelism if it sees that your CPU usage of your application is above 80% for about 15 minutes or so. And so this could be tuned with the use of CloudWatch metrics. We actually have a project to allow you to listen to CloudWatch metrics and scale your application based on other metrics. Maybe something having to do with the async function if you want to make more calls to your database or your API. That can certainly be achieved through the use of CloudWatch metrics. But out of the box, you will get the scaling based on CPU. And then lastly, you can run your Apache Flink applications on Kinesis Data Analytics in a VPC, making sure that your application is running in the secure way that you need your application to run, and you can control the traffic in and out of this VPC. So we can see some other CloudWatch metrics that we get, again, out of the box with Kinesis Data Analytics. We can look at downtime, the checkpoint size that we're making over the course of the application. And by default, Kinesis Data Analytics applications for Apache Flink are going to be making incremental checkpoints every minute. And that checkpoint is being made to RocksDB. And so that's configured for you. You actually don't have to set anything in your application code, and it can be disabled as well if you should choose not to checkpoint. We can also see the checkpoint duration over time, and these are important metrics to monitor the health of your application. Now, I didn't take any snapshots, but of course, you can create a snapshot just by clicking this button or by making an API call through the AWS CLI. Okay, and that's our presentation. So we just want to say thank you, and Hari and I will be available in the virtual Flink Forward booth later today to answer any questions you might have.